So hello everyone, welcome you all to this video. So as I've told you in my previous session that I have already completed module 1. So according to your syllabus, now the module 2 is about vector space and linear transformations, right? So when in our time it was module 3. So this is module 2 for you guys, okay? Vector space and linear transformations, okay? So again, the whole of the module 1 is been covered in my previous videos, okay, of vector calculus, okay. They are both the chapters, vector differentiation as well as integration. Detailed videos are available in this playlist only, okay. Around 15 videos are there. So those who have not watched it and those who are new to this video, please go and watch it, and please like this video, subscribe to our channel for the latest notifications and latest updates, okay. Please do that. So yeah. Let us start with this module now. In this, let us discuss first with the vector space. In that we are having first this subspace. Okay, what is this subspace basically? Let us discuss. Subspace is a non-empty subset of W. Okay, W is of any vector space or a whole any number. Okay, of a vector space V of F. Okay, this V of F is a vector space. Is said to form a subspace of V if W is also a vector space over the F, okay, with the same addition or scalar multiplication for V, okay. So what it means to say that is said to form a subspace of V, that is this W should be subspace of V only if and only if the vector space over F follows some arithmetic calculation such as scalar addition, scalar multiplication, etc. in this V, okay. So this is an example given here, that is, let W1 be a set of A, 0, 0 where A belongs to R, okay, where A belongs to set of R. Set of R is a set of real number. So the W2 is equal to A, B, 0 for values of A and B belongs to R, okay. Then we can say that W1 is a subspace of W2. Also W1 and W2 are the subspace of R cube, that is the third order real number set, okay. Yeah. So this is the basic definition of a subspace. So now we have some conditions for subspace. Under conditions we have first theorem 1. W is a subspace of V of F, that is a vector space. If W is a subspace of vector space, only if W is a non-empty set, okay, it should be a non-empty set. W is closed under vector addition, that is, if for all the values of W1 and W2, if it belongs to W, then W1 plus W2 also would be belonging to W, okay. It is closed under vector addition. The next condition is, it is closed under scalar multiplication, that is, if for all the values of A, if it belongs to F, then for all the values of W, it belongs to W, that is A dot W, that is under scalar multiplication, A multiplied by W, we would be getting under the set of W itself, okay. So this is the first condition, theorem 1. So similarly theorem 2, that is, if W is a subspace of V of F, if W is a non-empty set and for all the values of A, B belonging to F and V, W belongs to the set of W, okay. So then we could be saying the condition that A dot V, that is A multiplied by V plus B multiplied by W also would be belonging to W, okay. So this is the theorem 2 condition, this formula, okay. So you should be keeping this in mind. Related to this, in order to prove that subspace conditions and all, we have two important problems. So let us see that and let us try to understand, okay. Yeah. So this is the first problem. Show that W is a subspace of V of R, okay, where this is a vector space, where they have given two sub questions. Firstly, they have given the set of W as function of F that is f of 9 is equal to 0. In the second question they have given function of f, that is f of 2 is equal to f of 1. We should be showing that W is a subspace of this particular vector given, okay, vector space. Let us solve now for first one. That is this one, okay. Let us solve for this one. Since they mentioned here 0 and 0 belongs to a set of whole number, right? So we can conclude by saying that 0 of 9 equal to 0. So we can conclude by saying that W is that is the set of whole number is a non-empty set. Okay, so we can further go in this problem. So this is one condition proved here. Now let f comma g belong to the set of whole number. Okay, so if f comma g belong to the set of whole number, then according to the condition here they have mentioned f of 9 equal to 0 and g of 9 also let us take equal to 0 itself. Okay, now what we have, if this is the condition, then for all the values of a comma b belonging to R, we should be proving the theorem according to theorem 2. A dot f plus b dot g into 9 is equal to a dot f of 9, okay, plus b dot g of 9, right? So here a dot f of 9 we have written condition, that is it is equal to 0. Okay, so substitute that, plus b dot g of 9 also is equal to 0. Okay, so if we do the multiplication, we would be getting our answer as 0, right? So we got our answer in 0, so we can conclude by saying that hence a dot f plus b dot g belong to the set of whole number. Okay, so by theorem 2 we can say that finally W is the subspace of V of R. Okay, understood, right? Just try to understand. Now the second sub question. Here again the 0 belongs to the set of whole number, so we can write f of 2, that is 0 of 2 is equal to 0 of 1 equal to 0. Okay, so we could be saying that W is a non-empty set. The set of whole number is a non-empty set because it has the values from starting from 0 to infinity. Now again let the values f comma g belong to the set of whole number, that is f of 2 equal to f of 1, also g of 2 equal to g of 1. Okay, so if this is the condition, then for all the values of a comma b belonging to R, a dot f according to theorem 2 plus b dot g into 2 is equal to a dot f of 2 plus b dot g of 2, right? So now what is f of 2? F of 2 is equal to f of 1, right? So a dot f of 1 plus b dot g of 2 also is equal to g of 1. So now we can do one thing, that is a dot f plus b dot g we can take common, and 1 is common, so that I have taken outside. So we can say that a dot f plus b dot g into 2 is equal to a dot f plus b dot g into 1. So we can say that this conclusion satisfied. So we can finally conclude by saying that a dot f plus b dot g belongs to the set of whole number, right? So therefore the set of whole number is a subspace of V of R. Okay, so like this you should be solving this one simple problem related to the subspace and the set of whole numbers, okay, by considering the values of a and b. So note it down. So this is the next problem. Here they have given let V, that is the vector space, is equal to R cube, okay, be the Euclidean 3 space, and let the set of W whole number where the values of x, y, z belong to ax plus by plus cz equal to 0 where all these x, y, z belongs to the set of real number. Okay, so this is the condition given for W. Okay, and let a comma b comma c be the real numbers. So what we should be showing? We should be showing that W is the subspace of V. Okay, so how to show that W is the subspace of V? Let us solve and see how to do it. Let us solve using the second theorem condition. First, let U be equal to x1 comma y1 comma z1. Okay, and V be equal to x2 comma y2 comma z2. Let these two be any two elements of the set W. Okay, now what we can write first is, here they have given one equation, ax plus by plus cz is equal to 0, right? So here in place of x you write first ax1 plus by1 plus cz1 equal to 0. Okay, name it as equation 1. Similarly, we write one more equation, ax2 plus by2 plus cz2 equal to 0. Okay, so this name it as equation 2. Now use the second theorem condition, that is au plus bv is equal to a into, substitute the value of u, that is x1 comma y1 comma z1, plus b into v, that is x2 comma y2 comma z2, right? Now what you would be getting? Multiply a, so we would be getting ax1 comma ay1 comma az1 plus bx2 by2 bz2. So this we would be getting, right? Now you should be adding these terms, that is first term, second terms and third terms. So what we would be getting? ax1 plus bx2 comma ay1 plus by2 comma az1 plus bz2. Okay, this is the thing we got. Now since according to the given condition in the question, x comma y comma z belongs to W, right? So therefore au plus bv is equal to a into ax1 plus bx2, similarly plus b into ay1 plus by2 according to the question, plus c into az1 plus bz2. Okay, now just multiply. So what we would be getting? ax1 plus abx2 plus bay1 plus bby2 plus caz1 plus cbz2. Okay, now aax1, and here we have aby1, this term. Okay, and here we have acz1, caz1, acz1 is one and the same. So wherever a is common, right, to group it together. Similarly, wherever b is common, that is b ax2 and bby2 and bcz2. Okay, this term and this term I've grouped it together. So what you would be taking? Take a common, you will be left with ax1 plus by1 plus cz1 plus b into ax2 plus by2 plus cz2, right? So we have got this much, but you see in the equation 1 what we have written: ax1 plus by1 plus cz1 equal to 0 and ax2 plus by2 plus cz2 equal to 0, right? So substitute that, so we would be getting A into 0 plus B into 0. So if we do this, we would be getting our answer as AU plus BV equal to 0. So whenever we get equal to 0, we can conclude by saying that W is a subspace of V. Okay, so understood, right? So go through it again, see why I've written this equation U and V, just to show that W is a subspace of V according to the given condition here. Do that. And here, why I've taken A, B, C common, because in the variables they have given A, X plus BY plus CZ. Okay, and we are writing X, Y, Z in terms of second theorem, that is AU plus BV. Okay, so that's why in place of U and V, we should be substituting the values of X, Y, and Z respectively, and separately solving and doing until we get the answer as 0, because we should be proving that W is a subspace of V, right? Yeah. So let us solve one more problem. This is the next question. Let V be the vector space of all the square matrices over R. Okay, this is a question here. Determine which of the following are the subspaces of V. Okay, so this is the question, and there would be, here we have 4 sub questions. One by one I'm going to solve. This is the first sub question where the value of W they have given as one 2 cross 2 matrix, that is X, Y, Z 0, and it belongs to the variables X, Y, Z belongs to the set of real numbers. Okay, R. So let us try to solve it, and let us see which of the following are the subspaces of V. Okay, yeah. First, let it take one A matrix and write that equal to x1, y1, z1, 0. Okay, and take one more matrix B and write it at x2, y2, z2, 0. Okay, keeping this matrix as reference, substitute the values of one for A matrix as x1, for B matrix as x2, y2, z2 respectively. Okay, now these two be any two elements of the set W. Okay, now if A comma B belongs to R, then what we could be writing is A into A times A plus B times B equal to, that is multiply A with this term A vector, that is x1, y1, z1, 0 plus B into x2, y2, z2, 0. Okay, so after multiplying A to all the terms, you would be getting ax1, ay1, az1, 0 plus bx2, by2, bz2, 0. Right, now add these two matrices, so you would be getting ax1 plus bx2, ay1 plus by2, az1 plus bz2 equal to 0. Okay, so if you see here, this is of the form AU plus BV, right? A into U plus B into V according to the second theorem, and here we have one we have X terms, one we have Y terms, and one we have Z terms. And if you compare this with the matrix mentioned in this set of W, that is where we have the first element has the set of X elements, some X elements, here we have Y elements, and here we have Z elements. So we can say that this matrix is of type X, Y, Z, 0. Okay, so where in the question they are mentioned X, Y, Z belongs to R, so we can say that these three terms also belongs to R itself. Okay, where A and B are some constant values. So we can conclude by saying that A times A plus B times B belongs to the set of W. Therefore W is a subspace of V. Okay, so in the first sub question we have proved that W is a subspace of V. Okay, yeah. So let us get to the second sub question now. So this is the second sub question. W is given as the set of a matrix where matrix is a 2 cross 2 matrix again x 0 0 y where the value x or x comma y belong to R. Again in the similar way we should be solving. Okay, let A be equal to x1 0 0 y1 and B be equal to x2 0 0 y2. Okay, these two be any two elements of W. Now again take two variables a comma b, be some constant and it belongs to the set of real number R. So we can say that a times a plus b times b is equal to x1 0 0 y1 plus b into x2 0 0 y2. Okay. Again, if you solve like this, similarly we would be getting as we have solved in the previous problem, the same way. Let us see it how we could be solving it. A times a plus b times b is equal to, we would be getting again ax1 plus bx2 0 0 ay1 plus by2. Again it is of the form x 0 0 y according to the given condition, where in the first term we have all the x terms, last term we have all the y terms, right? So it is of the time this matrix, so we can conclude by saying that a times a plus b times b belongs to W. So we can say that therefore W is the subspace of V. Okay. So this was the second sub question. We have one more now, third sub question. I'll get to the question now. So this is the next question. The set of W, they mentioned A, and where this A belongs to the vector space V and A is a singular. Okay, we should be writing a singular matrix now. Okay, where W here is a set of singular matrix. Okay, in this question. So let A equal to one set of singular matrix, that is 1 0 0 0. Okay, this is a singular matrix, and B is equal to another one, that is 0 0 0 1. Okay, these two be two matrices now which we have taken instantaneously. Since determinant of A and B, if we take it, we would be getting this equal to 0. Okay, so we can conclude first by saying that A comma B belongs to the set of whole number. Okay, because if you take its determinant A and B separately, and you would be getting its answer as 0, because we have only one term, rest all the three terms are 0. Okay, so if it is 0, then we can say that these two belongs to the set of whole numbers. Okay, similarly let us take two variables again. If A comma B belongs to the set of real numbers, then A times A plus B times B, again same thing, A into A, that is 1 0 0 0 plus B into 0 0 0 1. So we would be getting multiply A 0 0 0 plus B 0 0, sorry, B into 0 is 0, right? So we would be getting A into A plus 0 is A, 0 plus 0 0, and 0 plus B B. Okay, so this we would be getting our answer A 0 0 B, right? So now take here whatever we got, right? If you take its determinant, if we get this equal to 0, then we can say that it is a subspace of V. But if we don't get this equal to 0, we cannot say that it is a subspace of V. Okay, because initially we have taken two matrix and its determinant equal to 0, so we can say that it belongs to W. But here if we don't get determinant as 0, then see, let us see what we will be getting. Determinant means cross multiplication, that is AB minus 0, that is equal to AB. So we can say that AB is not equal to 0. So therefore A times A plus B times B does not belong to the set of W. Okay. Therefore we can conclude by saying that W is not a subspace of V. Okay. Yeah. So this is the problem, guys. Question number 3. Solve it. So we have one last question. Let us see that. So this is the next condition for W, set of W, where A belongs to V and A square equal to A. Now they have given A square equal to A. So now how to prove this part? Again, now let A matrix be equal to 1 0 0 0. Initially I have taken one simple matrix 2 cross 2, so that they have mentioned A square equal to A, right? A square, if you do, that is multiply this matrix twice, 1 0 0 0 into 1 0 0 0. So if you multiply these two, you should be getting this matrix again. Okay. So how to multiply? Multiplication you don't know, right? First row and first column. Okay, 1 ones are 1 plus 0, then 0 plus 0. Similarly for second also we would be getting 0 plus 0, 0 plus 0. So we would be getting 1 0 0 0. Okay, that is A itself. So we can say A square equal to A. If you take the value of A matrix as this, you would be getting it would be satisfying this condition. Okay, so we can say that A belongs to the set of W. Okay, now consider A plus A, that is 1 0 0 0 plus 1 0 0 0. If you do add these, you would be getting our answer as 2 0 0 0, right? Now do its square, that is A plus A the whole square. Okay, that is equal to A plus A into A plus A. Now if you do its multiplication, we should be getting our answer as 2 0 0 0. Let us see we would be getting this or not. That is and if you do its multiplication, 2 2s are 4 plus 0, 0 plus 0, 0 plus 0, 0 plus 0. So we would be getting our answer as 4 0 0 0. If you take A plus A. Okay. Therefore we can say that these two matrices are not equal. So A plus A is not the member of the set W, because W is not closed under addition. If you do the addition part, that is A plus A, and if you take its square, we won't be getting the answer as same. We have just seen it. Okay, so it is not closed under addition, so we can say directly that W is not a subspace of V. Okay, so like this you should be proving this problem. So note it down. So yeah, that's all for this video. So please try to understand some concepts and do watch this video till the end. Okay, like, share, subscribe to our channel. Let us see some other concepts in the next video. Thank you.